So before we see more concrete examples, let's see slightly different form, which is quite useful even if you do lots of problems in PE. Like it's not always that the like this is the what is that called? Let me say this was the most simplest way how people control things. Okay, but there are many other ways of controlling things depending on what you want to control in the reduction. Okay, so let me give you one example. Okay, and then let's try to build the thing for this. Okay, so okay, we'll come back to this. This won't change, but other things will change. Okay. So suppose if I told you, look at a vertex cover. Okay. So faster algorithm for parameterized vertex cover. What does it mean? Suppose I have 2 to the power little of k n to the power big of 1 algorithm. Okay. That implies 2 to the power little of n algorithm for this. Right. What they will imply? Then what is this? ETH fails. Right. So in my world, because this is my assumption, and like what I'm going to say, if I will have a fast algorithm for vertex cover, and by faster I told you what it means, like I'm looking for what is input for vertex cover, g comma k, and the question is, does g has a vertex cover of size at most k, right? And suppose I have such an algorithm, and now I want to give a reduction from 3. So now what will I would like to give a reduction from 3 sat to vertex cover, for which I have assumed that I have a fast algorithm. So my black box now is replaced with what? It's a vertex cover black box. What does it takes? It takes g comma k. How much time does it takes? 2 to the power little o of k. We can fix it if we want really. So let's just for the sake of fixing it, let's fix this to be big O of k divided by log k, and let's say n cube. Just to be concrete, I mean it wouldn't matter anything. Okay, and this in time, this n cube time, it decides whether G has a vertex cover of size k or not, right? Decides. Right? Now, given a 3 sat formula, what should I produce? I have to produce an instance of a vertex cover, right? A graph and a number k, right? Okay. So it produces G and k. How much time can it take? You're trying to make an algorithm for which problem? For 3 sat, which is allowed to take 2 power little of n time. So how much time am I allowed here? More or less 2 power little of n time. Because now since we are talking in terms of little o, let's be okay, fine. But now tell me what k can take and what n can take. Right? Now we have two things, right? Number of vertices and this. Like what are these objects, right? Like because here the running time of algorithm is slightly it's very different form, right? So what should be the k and what should be the n? Okay, no, I'm not going to write because we agreed n cube. This is what it is because n is that little n for the SAT, right? Do you understand the question, right? Right? Yeah, it can output, but what all? I mean, what can it output? Huh? K by log k should be fine. So he says that k by log k should be order n, at most order n. What happens k by log k is n square? So suppose k by log k, all I can guarantee that k by log k is say n to the power 1.739. Then if I give him this, first of all, I have not even come to capital N, okay? I have not come to capital N, and this is something which you will come to that, I mean, right? But suppose if he said like 1 point something, then what does it implies? Okay, fine. So like, I would rather say forget log k. So k is like n to the power 1.739, right? Now, when I feed this algorithm, what is it going to return me? N to the power 1.739 by log n, some constant, right? 1.739 into log n. This algorithm is like more than 2 power big of n. So we cannot even hope to get a 2 power little of n algorithm, forget it, right? We cannot hope to get this, okay, fine. Okay, so n to the power 1.7 what, right? But what about say root n, okay? Some half will come here, so root n by log n. I have still not come on capital N, okay? Yeah, that's okay because that's 2 to the power little of n, that's fine, everything goes through. But then, yeah, if I'm able to make k being this much all the time, I'm able to show that k is less than or equal to root n, then actually, if I'm allowed to have k equal to root n, then do I need such an algorithm, right? Then I'm happy if I said to you, hey, come on man. In fact, then I can say that for to rule out if I'm in this reduction, I'm always guaranteed that k is root n, then I will say, let's make it k square. Now, what's the big deal about it? Because then also root n divided by some polylog which is 2 power little of, and I'm very happy, right? So this is where the tightness of this comes. So when you assume something, right, you take a parameter to be really close to each other, right? So I mean, that's the power of the reduction, because when I assume something, for now imagine if I wanted to rule out k square by log k algorithm, k square by log k algorithm, my k cannot be more than root n, right? Okay. So for now, I will come back to log k. So basically, everybody is right. The best thing is to take this and compare with whatever the n is. Fine. So all we want is k log k. All we want is k divided by log k should be less than or equal to n, right? This is all that we want, some constant type. So basically you can assume that k is like roughly like n log n, and this will be fine. So if I set k equal to n log n, nothing would change, right? I had this algorithm, right? This is what I have a fast algorithm. So even if I set k equal to n log n, what will happen? If I set k equal to n log n will get cancelled, and no, I cannot take n log n. I have to take slightly smaller something. So I will take 1 minus epsilon, right? Then definitely, right, there is a log n here, and there is something smaller. So this is 2 to the power little of n algorithm, right? Because now let's see what will happen. 2 to the power big O of n log n. Let's see, 1 minus epsilon n log n, right? Right. So it is like 2 to the power big O of Did I do something wrong? Sorry. Yeah, this is what it is, right? Yeah, so this becomes, sorry. So this becomes log n power epsilon. If epsilon is positive, this is little of n, so we are happy, right? But if I just put log n, then log n will cancel and get 2. So you have to be just careful with these little things, right? So k can be as much as n log n if you are ruling out smaller thing, right? So for example, if I was saying, so what, suppose I said, oh, it does not have little o of root k algorithm, right? Then what am I allowed? I say, okay, fine. So essentially, root k should be less than or equal to n. So k should be less than or equal to n square, right? So I just choose something which is slightly smaller than n square, asymptotically. Like I choose any function which is asymptotically close to n square, and I'm still fine, right? So this is how you carry around the parameter, right? But imagine yourself, if I say vertex cover is an example, it's not something which is, it's for the illustration, okay? Suppose I wanted to rule out that this guy does not have this algorithm, 2 to the power little of k algorithm. No, this is not possible. Then what is the value of k? I'm allowed. Look, I want to rule out this algorithm, right? Then what is my value of k can I take? Again, I don't have to do anything. Let's look at what it is. Okay. So this 2 to the power little of k should be less than or equal to somehow n, right? So, or some little, right? So what is this? So basically it's like if you take log both sides, so what you will get? You will get something like little of k is log n. So roughly k should be like log n, right? So what happens if I set say k equal to log n 1 minus epsilon? I choose, right? Now if I do the maths, what will happen? So now I run this algorithm with this parameter, then 2 to the power little of k is nothing but it will be 2 power little o of log n to the power 1 minus epsilon. So what is 2 to the power little of 2 to the power little o of epsilon? This is nothing but something like 1 n to the power 1 minus epsilon, right? This is like some n to the power 1 minus epsilon, because 2 power log n is n, right? So 2 power, I mean, rather than saying n to the power 1 minus epsilon, let's say 1 minus epsilon. I think this itself will be great for us, not like some n to the power 1 minus epsilon. K is like log n of 1 minus epsilon. So now what is 2 power little o of k? So it is going to be something like little o of n minus epsilon, which is like 2 to the power little of n. So all I'm saying that bigger the function you try to this, smaller the parameter will become. Smaller the function you want to rule out, bigger the parameter you're allowed to choose, and that's a game which you have to play. So these are the conditions which makes the reduction hard, right? I have to control so many things at the same point of time, right? And that's not easy. So okay, so now we have understood how k could be, right? Now k could be anything, right? K is the solution size here, right? But k could be anything for a minute, okay? Fine, but now let's go back to n. What n can be? I know that this algorithm runs in n to the power 3 times, right? What could be n can be, right? Again, world is not very different. You just compare. Okay, fine. What do I want? Nq should be to the power little of n, because 2 power little of n times 2 power little of n time is some 2 power little of n time. So what is n? Nq should be to the power little of n. So how much n is allowed to be? No. N cube. N is the size of the instance. N is vertex set of G. These are two different things. A graph can have many vertices, but the parameter could still be small. It has nothing to, even with respect, even if I want to rule out 2 to the power little of k, what can be the n? I know that my k has to be something, but what nq can be? Well, nq should be at most 2 power little of n, which is nothing but n should be 2 to the power little of n divided by 3, which is still little of n. So n can be as large as 2 to the power little of n. So my instance can be as large as 2 to the power little of n, but the parameter has to be as small or big depending on what is the function we are trying to rule out, right? So graph can be large, and we exploit this all the time when we make reduction. Graph could be very huge, but the parameter of question is under control. I'll give you one example here. Okay, so fine. So this is what it could be, as bad as this. But suppose, for example, here it is, FASTA algorithm for vertex cover parameterized by tree width. Okay, those who know tree width, it's fine. If you don't know, just don't worry about it. What is known? So the parameter is no more solution size. Parameter is tree width of the input graph. And what is known for this algorithm? Okay, what is known for this problem, that you can have an algorithm which is running time 2 to the power tree width dot n. You can find a minimum size vertex cover in time 2 to the power tree width dot n, whatever this word means. Okay, and now what I want to show, that if I will have 2 minus epsilon time tree width time some n power c algorithm, it does not matter how c is, then I will be able to get 2 minus delta to the power n algorithm for SAT. Basically I am saying the set fails, right, because SAT I am not quantifying with 2 or 3, all I am saying is just SAT, the last quantifier. Now tell me, if I have to make such a reduction from SAT, how much time am I allowed to take? What should be the instance now? And what should I need to control here? What is the something which I need to control here of G? If I want to rule out such an algorithm, what I have lot of things to compare, right? So now instance has, still it's a vertex cover instance. So I'm looking for, does G has a vertex cover of size at most k, but the parameter of my interest which I'm trying to find lower bound for is not k, it's a tree width of the input graph, right? So Gk and what? So now when I give a reduction, I'm taking 2 minus delta to the power n. So fine, let's not worry about, I can take this much amount of time because anyway it's production time plus, so everything adds up, so it's perfectly fine, we take this much, or some delta prime which is strictly less than delta is perfectly fine. So I'm allowed to do this much amount of time. But now let's look at the graph which we are going to produce. If I want to rule this out, what should be it? Right? G right, it is any n to the power c. So now we have to control vertex set of G and tree width of G, right, because that is a parameter of interest. Now what we know, that well what is my tree width should be? Okay, 2 minus epsilon power tree width, right? This is what my algorithm running time is. It should be greater, it should be less than equal to 2 minus delta to the power n. Now there's an epsilon, there's a delta, right? To make our life easier, let's also call it epsilon. Just to make our life easier, it doesn't matter, right? Then what does it tells us? Huh? Tree width should be n. So in this reduction, number of variables, graph could be, I don't know what it could be huge, it could be small, it could be big, I don't care. But the tree width of the graph is a linear function, not even any linear, it is n. Because if I had 2n, then I am lost. I will tell you in a minute what I mean by that if we had 2n. So in this reduction, okay, first of all, what is tree width? Suppose all I can say the tree width of G is 2 times n, where this n is the same n here, right? And suppose capital N is, I want to rule out n to the power c. So what can be the capital N be? Right? For now, suppose even if I had a poly n, not even very big size, like a really small size graph, but tree width is 2n. What can you rule out then? Can you rule out this? Can you rule out this algorithm then? Because then if all I can produce is tree width of G is at most 2n, then I cannot rule out this algorithm, because then this algorithm, when I run this guy, forget about this, it is going to take 2 minus epsilon and tree width of this graph, which is 2n. So it is going to be 2 minus epsilon the whole square, 2 minus epsilon the whole square, 2n. It rules out nothing. So for example, this is 1.999 whole square. So just to be even more concrete, say 1.99. Okay. So if कोई बेच रहा है कुछ, okay. So lot of things are very delicate. Now what you are able to do it, then I can only say that, well, then 1.99, a square root of 1.99 to the power tree width is not possible. This I can say for sure, because if I do this, then I get whatever I want. If I am telling you that, okay, all I can rule out is this, because a square root of this is still 1.99, and that's an running time for my SAT. So everything, because I'm trying to make an algorithm for SAT, I look at SAT, what form of the running time it needs, and based on that I fixes everything, right? So now if I wanted to rule out tree width, this reduction must make a graph with tree width at most n. 2n is not allowed. Any alpha n is not allowed. Then what do I have in LA? You have more thing. You can have log n, because 2 power big of log n is polynomial in n, so that's okay. That's the only thing. So when you make such reduction, how much control you have to be, you have to imagine yourself, how much control you need to be. Yes, you have a lot of time, but the instance which you have to produce, the tree width of the graph is literally same as the number of variables in my input formula, right? Now indeed, now if I have some n to the power c, now I have to be careful, I cannot be anything, right? So my now n has to be, now what is my n? Okay, fine. Look, but how much big the graph I can make? I mean, for all affection and love, we can make n. What is this? I want n to the power c should be less than equal to 1.99 to the power n. So n has to be less than equal to 1.99 to the power n over c. That's it. So the graph can be as large as this. It's huge graph, right? So now basically all you are trying to do, even if you have a multi-parameter, so it means, okay, but SAT has only one parameter, what is number of variables, right, with respect to which we are trying to do. So now this n in parameter it goes something, instance size it can blow up something. So for the same instance, look, for the same instance graph is as huge as this, but the other guy on which you are trying to bound the running time is this, okay. Now let's see one concrete example of such a reduction. Yes?
So if n is very small, say 1.99 to the power some minus n by c, but then we can have 3 width to the 2n, and we can have a very small instance.
No, come again.
So 3 width,
you can make delta
I mean we can have 3 width to be 2n say, and then this n to the power c, is 1.999 to the power n by c, say it is negative.
Yes.
To the power minus something, then we can have this 2n.
Sure.
Cancelling out.
Yeah, 100%.
Very small instance with
But what is whatever that is, that's not going to negative, right? That's not going to be fraction. Imagine yourself, right? You have some form of running time, and n to the power c has to cut this off, right? I mean,
you will get a fraction like log 2 minus epsilon to base 2 minus delta.
something. And I'm not, look, all I'm trying to tell you, yes, anything is possible. You have a form of the running time, just see what you can do. And in fact, what I said is also not correct completely, okay? It's not completely correct because look, the running time of my algorithm is a multiplication of this and this, right? So now I allow, so I cannot take 1.99 to the power n. Now if I say n by c, right, then what is this? 1.99 to the power n over c into c, right? So like this is going to do, no, not sorry sir, this is not allowed. And in fact, if I allow this to be this, I cannot allow it to be any function of n. Like this size cannot be any exponential function of this. This has to be at best some to the power any little of, so that this just adds up and we can for any extra constant we can. Because even if you had n by 100 and you have allowed yourself this much time, it is at least n plus n by 100, right, which is something more than 1.9. Of course you can play with some epsilon delta and play the game, yes you can do that, those are allowed things, but you have to be careful. Then you will put much more constraints on what you are allowed to. Now imagine yourself, you are making a reduction where every bit, every vertex of every variable is basically has one bit to represent itself, and together they can have some log n bit, okay. Imagine yourself that now, suppose yourself I had dominating set here, 4 coloring parameterized by tree width. Everybody knows there is an algorithm with running time 4 to the power tree width to the power n, and now I want to rule out tree width. Now tell me what should be the tree width of G to rule out this? It should be roughly n by 2. So one bit, like one variable doesn't even get a bit to express itself, it's like a half a bit. Look, if I want to rule out this algorithm, now my tree width has to be much smaller, it's like n by 2, because then this to the power whole square, right, because this to the power, why? Because look, I am going to put this to the power n over 2 and that should be less than equal to 1 minus 99 to the power n. That's it. So from where do I get these things? No, it's not magic, right? Let's try to see how do you get these kind of things. So this should be less than equal to 3.99 to the power tree width should be less than equal to say 1.99 to the power n. That's it. Solve this. You take log both sides, what will you get? Tree width log 3.999 should be less than equal to n log 1.999, right? So tree width is basically n into log 1.999 divided by log 3.9999, and I have taken log with respect to base 2, so this is roughly like half, right? So that is all that you're allowed. So I just solve this. It's not that I come up with these numbers from somewhere. No, I just solve this, whatever I need, I just. And it's amazing to note that there are actually, you don't need this, you need polynomial time and produce an instant g of k. V of g is poly in n, polynomial time such that the tree width of g, for if you are giving a reduction for vertex square parameterized by tree width, you can come up with n plus big O of log n. And if you wanted to rule out some q minus epsilon time tree width, then you can come up with tree width of g is, I think, n log some base some q or something. I think this is what you will get, right? You can come up with such like q coloring for fixed q, like 100 coloring. You can come up with this, yes, plus big O of log n. So there are such a reduction, and we will see such a reduction in this course. But let me give you one amazing reduction. Okay, okay, and then we will go concretely into like some other problems. Okay, we have built up something. Let me give you one interesting reduction, but very easy reduction, and then we will see. Then we will go into the. Then after this, we will just follow linearly and try to build something. Okay. So what I'm going to show to you. All of you know this problem, hitting set. You have a universe of 1 to n and family S1, S2, Sm, right? Where Si is a subset of U, objective, given a number k, objective. Does there exist x subset of U mod x less than equal to k, mod x less than equal to k, and x intersection Si is greater than equal to 1 for all I in M, 1 to n. Okay, this is. Now my parameter of interest is n, side of the universe. Do you see any trivial algorithm? Try all possible subsets, right? Even if I would have asked minimum, that also you could have done, right? I try all possible subsets of my universe and check whether it is a hitting set or not, right? So 2 power n is definitely possible. Now let me show to you that we cannot do an algorithm with running time 2 to the power n over 2 and poly in n plus n, right? Not possible. Okay. How do we show this? Okay, so I want to show under third. So I have to starting with sat, I have to give a instance. Let's see, what instance do I need to create? Okay, I need to create universe, family, and a number k, right? And here I have a black box, which for what? Hitting set, parameterized by n, okay, universe size, whatever the universe size, let's not write u, let's call it universe size, okay, and this algorithm will run in time, say 2 minus epsilon to the power n, and that's it. Well, let's not worry about anything else. Okay. Universe size divided by 2. Yeah, universe size divided by 2. This is what my black box is. What should be the reduction? So I'm going to give you a polynomial time reduction from SAT, which is very easy. Okay, so what is SAT? So SAT has, given a formula SAT, I have C1 or C2 or Cn, right? This is what my SAT formula is. My universe is x1 comma x1 bar, xi comma xi bar, xi in the variable set. So my universe is nothing but all the literals. So what size? It has become 2n, right? Now what is my formula? What is my family? Family is take clauses as a sets, right? What I mean by this, so xi, xj, bar, xk, xl, not k, xt, xl, if xi or xj bar or xt bar or xl is a clause, right? So I think each clause as a set of variables. Forget or, it's like a set of variables. Okay, it's like I can also think of what is a hitting set. I have to pick one from each set, and what a SAT does, it sets true to every clause. So I'm just picking those guys. So that's the way to view SAT. Now I need to ensure consistency. Like I don't want to pick both xi and xi bar. Then what do I will do anything? So you add union xi comma xi bar. Okay, I going from 1 to n. So this is my set. So I have also added this tuples. And now what do I set k equal to n? I set k equal to n. Okay. Now let's look. If I had a hitting set, if I had a satisfiable assignment, then if I have a satisfiable assignment, then there is a fee. If there is a satisfiable assignment, then there is a fee from vertex set to 0, 1, right? Vertex to 0, 1, right? Now what is my hitting set? What is my hitting set? Well, what I do for families is that look at the guys which are set to 1. Either xi is set to 1 or xi bar is set to 1, like in this assignment, right? So just pick those guys, those literals which are set to 1, and that's it. That has size exactly equal to n, because phi will set either xi is 1 or xi bar is 1, right? Now if this is a satisfying assignment, then for every clause someone is set to 1, right? Either for some variable this, so everyone is hitting, and these two things which you have set, they by choice are hitting set. So forward direction goes through. Now reverse direction, the proof is very simple. Fine, I have to show that if there is a hitting set here, then there is a satisfying assignment here. Fine. So suppose there is a hitting set here. What is its size? N. So can from this 2 tuple, can he pick both? Because if he picks both, then his budget goes away. So he picks exactly 1. So that's consistency, right? So whatever it has picked, right, you set them to be 1. My claim is that's your hitting set. Yes, that's your hitting set. But where did n go to? To n, right? So that is why you are not able to rule out. So this is a simple reduction. Okay, this is what we started with long time back, and we thought that okay, fine, this looks cool. Okay, and this will give you 2 minus epsilon to the power n by 2. Okay, somewhere in the middle of the course, I'll give you a reduction which is extremely difficult. Uses all the, it's like polynomial time reduction, right? It's polynomial time reduction. It uses all the power of satisfiability, and it will rule out this. So there's a very non-trivial reduction from SAT to universe parameterized by hitting set, which will use all the power of running time here. It will run in exponential amount of time and produce this nicely that everything goes through. Okay, but that's for some other day. This is just to give you a brief, like what all things can you prove, right? Using set, this is the first reduction you have shown, that using set, if I believe set, hitting set parameterized by universe side cannot be done better than 2 minus epsilon to the power n over 2. Okay, I will also give you another beautiful reduction, which is the base of lot which followed later in a minute. Okay, so all is well. Okay, now what I'm going to teach you is how to make these reductions. So I have told you What kind of reductions do you need? This. What I have not told you also, that there are reductions of several kinds. In these reductions, I have only worried about instance sizes, parameters, running time, and all this. There are also reductions which needs to take, for example, accuracy. For example, the reductions which are used in approximation. Well, certain factor goes to certain factor, so you also have to take control of accuracy, right? Imagine accuracy, running times, okay. There are also reductions which needs to take care of log space, right? Log space reduction. So you cannot make any of these reductions, but you have to maintain certain space requirement. So any complexity classes, okay, any complexity classes or anything where you want to make a reduction, it is nothing but you look at what resources you are allowed. Reduction just means you are able to convert a problem A to a problem B, not going beyond the resources which you are allowed to use. That's it. If you remember this in your life, there is nothing called reductions. You don't have to remember any reduction. Well, I have to convert a problem A to problem B, maintaining certain requirements, and that's it. Just maintain those requirements, and that's your reduction, right? It could be time, it could be space, it could be accuracy, it could be anything, right? So I don't have to read a definition of what the reduction log space. No, I don't care, because all I care is that from here to here I have to go. Allowed space is this, allowed time is this, right? Allowed accuracy is this. Now you do it, right? Depending on what I need, I just go ahead and do it, right? So this is all about being in the time constraints, space constraints, accuracy constraints, or whatever constraints you have imposed yourself while doing a reduction. And what is a reduction? It is nothing but given an instance of one problem, creating an instance of some other problem, satisfying certain properties without changing the answer, right? In most of the things which I have been talking about, without changing the answer. Meaning, if I have given you a yes instance, you should be giving me a yes instance. If I have given you no instance, you should be giving me a no instance. But not all reductions has to do this. There are also something called gap creating reduction. When it says, hey, in hardness of approximation, hey, when I am yes, you are really very much yes. But when I am no, you are far away from yes. So this gap between I am very much yes and when no goes to far away, this gap which we create between this and this, what I mean by this? For example, I will tell you that if SAT is satisfiable, so suppose I am trying to give a reduction from satisfiability to max satisfiability. I want to satisfy maximum number of clauses. I said I will give a reduction with the following property. If my input formula is satisfiable, then the output formula is always satisfiable. But if my input formula is not satisfiable, then at most one clause is satisfiable. Suppose I am able to create, I am not saying you can create such a reduction, but then you have created a gap of how much? Like one and all, right? And if you can come up with such reduction, then probably you will be showing that, oh, then this problem does not have any approximation. Like it's like even n approximation is bad, because then I can do something funny. But what you can say, sometimes you can say, well, all are satisfiable, but when it is not satisfied, number of clauses which I can satisfy is at most half. So there is a gap between yes goes to really yes, but no restricts itself to only half. So this gap, so now imagine yourself having an approximation with factor 3/4. You will be able to distinguish between this and no by running this approximation algorithm in between and check between this. So if you are able to create such gap instances, then you can do something more fantastic, fabulous. We'll come to those reductions at the end in context of lossy kernel, because we need to make such reductions. Not only polynomial time preserving, we have to also create gap and preserve them. Okay, but we are not going to go that. For now, yes goes to yes, no goes to no, and we learn how to make reductions. Okay, so that's the bottom line, right? How to make reductions. Okay, now I have told you that there's nothing big happening here. Now I have grouped my lectures based on what assumptions do I want to use, and based on those assumptions I am going to show you reductions. It could be from a polynomial time problem, it could be exponential time problem, it could be anything, but it is based on the assumption which I plan to use. That's it. Okay, so this is how I have grouped them. Okay, so in whatever time little we have, we are going to see I first want to teach you, like, there's nothing which starts. If you don't know how to make an NP hard reduction, it's very hard to make any other kind of reduction. So first, we go back to the NP hardness reduction and look at some basic reductions and why the reductions are the way they are. Like no one creates them, you create those reductions because there is a meaning associated with everything. If you understand what you are trying to make from those meaning, you will be able to create those reductions. Okay, all well? Okay, fine. So now I'm going to rub everything and just going to do some simple NP hardness reduction. Okay, whatever I was telling you was a philosophy of reduction, but now what I'm going to do is concretely, so do some NP hardness reduction and show you some beautiful properties of those NP hardness reduction and what it actually already proves, okay, under different assumptions. Okay. So I'm going to give you a reduction starting from 3 sat, okay? If your brain does not work, which problem to start from? 3 sat is the right problem to start from. If you don't know which problem to start reduction from, 3 sat is the right problem. My general homework assignment usually is look at Kleinberg and Tardos and make every reduction starting from 3 sat, because actually I sat down once and actually did. It is possible to do. It's hard, but it is possible to do. But once you do this in life, you never forget how to make reductions. But for those things, you have to work harder than what teacher asks you to do. Okay. So 3 sat, there are two ways of viewing 3 sat. Okay. Okay. What is this? So what is generally a 3 sat formula consist of? It consists of phi, right? Clauses, m clauses, and variable set x1 to xn. Okay. Now, the two natural way of looking at SAT is, look, what is my goal? My goal is to find a satisfying assignment to this, right? So when I say I'm giving a reduction from 3 sat, it means I'm making an instance of 3 sat into something, right? If I'm giving a reduction from, say, 3 sat to some problem pi, it means I'm taking an instance of 3 sat and converting it into an instance of pi. Now, just now we saw one way of looking at it. What is it? You look at each clauses, it's like a selecting variables, right? Selecting variables from each clauses which are consistent and which ensures correct. Like what I mean by this, look, whichever variable you set to true, it's like selecting that variable and making them to be true, right? So it's like, this is what I call selection understanding. What is this called? In my head, it is like selection, right? It's a selection way of doing. Let me see what I write here. I could have written something more when I was making, okay. Okay, so what does this mean? Selection, like pick terms from each clause, okay, that are consistent. Okay, if you're able to pick a variable from each clause which are consistent. By consistent, you're not picking xi and xi bar. Then you have your selection. Then you have an assignment. Just set these guys to be true, right? If you have a subset, this is what I call hitting set view of this. Is that you are picking a variable, picking a literal from each of this, so that they're consistent. You're not picking both xi and xi bar. That's you. So pick terms from each clause that are consistent. That's one viewpoint. And whenever you're looking for subset and this and that, this is the greatest view. This is the beautiful viewpoint to have. And the another viewpoint is what I call independently set variables 0, 1. Okay? Right? Independently set variables 0, 1. Like decisions do not depends on other. Okay? Okay? We just now saw an example of this. This is exactly what we saw when we gave a reduction from SAT to hitting set. We were selecting variables coherently. Now, what does this mean? Okay, you will see enough examples of this. Okay. 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 So now let's give a reduction. They're too simple reduction, not something which is very funky or something. Okay. So what I want to do, 3 SAT reduction to say vertex cover and 3 SAT to independent set. Okay. So let me do this. Okay. What does the clauses means? Right? Suppose I want to have this viewpoint. What does the clauses mean? Select from each term, right, such that something happens. Okay. So what I do, suppose I have a clause Ci, which is xi, okay, or xj bar or xl. So you just do very simple thing, which is you want to select, right, but you want to create a graph, right, and in some sense I want to say from here I must select one guy. I want to say this, right, I want to select someone. Okay, so I just do the simplest gadget which I can draw for selection. Okay, so this is, let's call it t. Okay, so I will call this variable t, and on the bottom I will write I, j bar. Basically for every literal, I do not want to call it xi because then other triangle also I will be calling xi if it occurs. Okay, and here what is this? I, j bar, and there it will put it L. Right? I mean, ideally you would like to put it xi, xj bar, xl. Fine, I don't care. It makes it different because there's a V and there's a T. Fine, it's a vertex. So I made triangles for every clauses. Now you need to be consistent, right? That are consistent. How will you ensure consistency? It's a problem. What problem you are reducing to? Independent set, right? What is the best way to ensure consistency? Huh? What is the best way to ensure consistency? Exactly. So you look at every copy, right? So now xi can be occurring in many triangles and xi bar will be appearing in many triangles. Okay. So xi appears in many triangles and xi bar appears in many triangles, right? And I do not want to pick, if I pick this, I want to preclude picking anybody else. So what you do? You make a complete bipartite graph. Now because if the moment you pick this in the independent set, you rule out picking anybody else from here, right? If you pick one from here, you rule out picking anybody else from here because everybody is named. And that is my end of my reduction. But now what is, I have to set the size of the independent set. Size of the independent set is m. So what I want to say? So given a phi, I have done this. So I have given phi, I constructed a graph G, okay, the way I described you, and I have n, m, where m is the number of clauses. So I say phi is satisfiable if and only if G has an independent set size m. Okay, fine. Look at the forward direction. Forward direction, it means there exists a function from such that alpha satisfies phi, right? It means from every clause, at least one literal is set to true, right? From this, let's go and pick them up. Okay, pick vertices corresponding to literals that are set to true, by alpha in each triangle. Okay, now you can ask two questions. Hey, it's possible that alpha may be setting two guys to be true. Just pick one arbitrarily. Do not pick both, right? If in some clause there are more than one literal, it's set to true. Restrict yourself to exactly one. Okay, it's possible that when I set, there are two literals which are set to true, right? I just take one from each of them and I've got. You look very confused.
So the M is just a lower bound, so this case is possible.
What?
We are looking at an independent set of size at least M.
Yes, but that should be independent set. Right? If I pick two from here, that will not be independent set. Yes, this is true, but yes. So now, for sure, from every triangle, I have picked one and exactly one. Now I have to show, of course, all I have to show that, of course, that there is no edge between them and them. But why? When did I put an edge between them? If this guy was a, what do you call? If this guy was set to be xi, and the other guy was xi bar, it's copy. Right? Then only I set to be true, right? But alpha has no such property, right? Alpha is only setting only one guy to be true. So these edges ensures to us that this is an independent set in the forward direction, because that's the only edge which I have put in my graph. For the reverse direction, right? Look, it has an independent set of size at least m, right? If it has an independent set of size at least m, what does it mean? From every triangle, it must pick one vertex each. Because, and what did you use here? Budget. So there are things are in your control. What is this? Budget. In reduction, budget has a great role to play. Okay? If budget would not be there, then you are dead. Okay? So I also use budget cleverly every time. Right? So for example, now it has an independent set of size at least m. Okay? So for the reverse direction, G has an independent set of size m. What does this implies? From every triangle, we pick exactly one vertex. Okay, exactly one vertex. And what does this edges implies? What does this edges implies? That if I have picked a vertex, I have not picked its copy. It's an independent set, right? So from every triangle, we have picked exactly one vertex, right? Let V star be the literals corresponding to these vertices, right? So it could be there were 10 vertex which correspond to the same literal, that's fine. So V star be the set of literals corresponding to these vertices, right? Claim V star intersection xi xi bar is at most 1 from every variable, and it's like its and its copy, it picks at most 1. It cannot pick both, otherwise this cannot be an independent set. If it had picked up both, it means you have picked up 2 vertices in the independent set, right? But there is an edge between them, because from every copy and its partner I have put an edge. I made a complete bipartite graph, right? So this implies at most 1, right? Okay, and what is your alpha? Alpha sets V star to 1 and remaining to 0. That's it. That's it. That's your assignment. And why it is a satisfying assignment? Well, it is a satisfying assignment because every literal was part of each clause, right? So go, you have set them to be 1. So this is your reduction. So what viewpoint? So from every clause, they picked up 1 person, but now since you are picking something from every clause, right? So these are independent, like they are independently picking something from each clauses. So now you have to be consistent, right? That you are not picking xi and xi bar from somewhere. So if I decide to pick xi from one clause, right, you are picking xi from every other clause, because xi either, like what I mean by picking, when I am picking, it means xi is set to 1 and that is used by setting it to be 1 to satisfying that clause, right? Then it can only satisfy other guy if xi has been set to 1, it can only satisfy the clauses where it appears xi, not xi bar. But if I have selected xi bar to be part of my solution, it means xi bar, xi is set to 0. So wherever xi bar appears, it is setting those clauses to be true, right? So I only want of one kind, and that's great, okay? And this is what the job it is. So this is what I mean by consistency, because anyway, you need literals in only one form to be useful, right? So they have 2 states, one as a xi, as a xi bar, but for us, they are only one kind that they are useful, okay? Okay, now I am going to do independent choices. Now what is an independent choices? So now whenever you have an independent choices, what does it mean? So first thing to understand is, I will do the second reduction and then you will see, I mean I could have done a reduction from here immediately, but in independent choices what happens, the first thing to look, for every variable we have a gadget. What have? We have a gadget. For every variable we have a gadget which are identical. It's not that for this variable gadget is different and for that variable the gadget, no, they all are identical. And your objective is that these gadgets had states, right? When every gadget can have several states, but for now every gadget will have 2 states. One state will mean, oh, what I mean by gadget has a state, oh, if gadget is picked like this, then it means 0. Gadget is picked like this, it means 1. So since every gadget has 2 states, how many states it has? 2 power n. So basically you are, whenever you are doing independent random variable, sorry, independent variables selection gadget, then it is important for you that there is a bijection between your all set of assignments and all possible, what you call, states. And then you put up the clauses in a way that only truth, only those assignments which set it to true propagates. But in the beginning, all possible choices should be allowed, because we don't know what alpha is going to look like, okay? So now this is what it means to be. So let's give a very concrete example. What should be such a gadget for vertex cover? Now I'm going to do a reduction from vertex cover. So again we are given phi, Cm, right? So now for each xi, I have to make a gadget. What is the simplest gadget that I can ensure from the vertex cover, and by picking them, I know that I have both choices. And the simplest gadget is an edge, right? So for every one, I make an edge. What is this? And I mark them, x1, x1 bar, x2, x2 bar, xn, xn bar. Now notice, what does it represents to? You fix an assignment, any assignment. You fix an assignment that means that, which means selecting those variables from each of them, and that's a vertex cover, right? And you need one from each of them. So this is what I mean. You can independently choose which one you want to pick, xi or xi bar. It does not depend on anybody else. So right now, so up until now, you give me any assignment, I have a way to select these guys, right? So if you gave me, you set it x1 bar equal to 1, x2 bar equal to 1, x3 bar equal to 1, then I will pick this vertex, this vertex, this vertex, this. So I can, what do you call, so there is a bijection between the states which are allowed, right, and the number and all the assignments of these variables. And now, but now you have to add gadgets corresponding to clauses such that only assignments which are set to be true, like which satisfies the formula, can get propagated, right? And that is just something which is the role of clause gadget. It's not the role of variable gadgets. The role of variable gadgets is only that every possible assignment there is a way to choose. So like it provides you in some sense a bijection between state space of your gadgets versus assignment. That's it. It's your clause gadget whose job is to ensure that if I start with a satisfiable formula, then only satisfiable guy can propagate. If I start with an unsatisfiable formula, nothing can propagate, right? But they in themselves should be able to do all the job, right? So this is what, so this is like, and this is how we make most reductions largely. For each of them we have this, and now we try to add gadgets corresponding to each clauses to maintain this propagation effect of what is that called, of the assignment which are set to true. So what we'll do here, it's very simple. Let's fix some clause. Suppose some clause Cj, say let's call it x3 bar, okay? Suppose this is what it is. Say Cj is say x1 or x2 or x3 bar, okay? So what I do, I make a triangle corresponding to Cj, okay? Make a triangle corresponding to Cj and name them with what? Xi, I mean, I'm being, because now I don't care what they are called, because anyway I will get all my assignments from here, right? So I don't care what I call them, because anyway these are useless people. Xi, x2, x3 bar, okay? Now let's think about it, okay? Any vertex cover must pick one vertex from here because they are matching edges, right? So whatever I do, my budget for vertex cover k is at least n plus. Now whatever I do, can I cover all these three edges with one vertex? No. So two vertex. I need two vertex. Okay, so I will have 2m. This much, like by drawing this much, I have added this much to my budget. I cannot expect anything more, right? I might have to add more based on what edges do I add. And what edges do I add? So what is my intuition? What do I want to say? Think about it. So what does it mean? Look, it says to us that once I have fixed these things, it says to us, look, xi, look at it, what does this say? Look, either I have to give somehow edges between them. Look, that I would like to somehow leave someone from here and let that guy be taken care by somehow from your assignment. How do I ensure this? That, because look, someone I will be picking up here also because I have to pick this, right? And some people I have to pick here, but I want to give an edge in a way that the people who's here is able to take care of some things, because two people from here will be able to take care of any vertices goes here, but one person cannot take care of. If I force you this much is my budget, then one vertex cannot take care of the edges corresponding to it, so it must be taken care by the other side, right? Because any two vertex will take care of all its edges, and you have to pick two from everybody else. Okay, so now this is very simple. This is x1, so you make an edge to x1, x2 you make an edge to x2, x3 bar you make an edge to x3 bar. So this is what you do. Now what have you ensured? So the moment you pick x1, right, the moment you have picked x1, the edge corresponding to x1 here or everywhere will be taken care of it, right? All you need to ensure, notice that whatever the selection of vertices are here, when I delete them, what is left? First of all, everything is left, and what is left is nothing but disjoint union of, like what is left is triangle where one vertex there is no edge. Then I am happy, because then I can pick the other two and take care of everybody else. All I want to do achieve is this. This is all that I want to achieve, and this is my end of my reduction. Why? Because suppose I had a satisfying assignment. If suppose I had a so what I would like to show. Now look, here again budget plays the role. Budget will play the role because you will have to leave one guy in the reverse direction. You cannot be picking all the three guys, because your budget is so tight that you have to pick n from here. You cannot be picking all the three from one, then you don't have a budget for left, because locally everybody needs two in the triangle and every matching needs one. And what is your budget? N plus 2m. So what I would like to show, if and only if here k, which is n plus 2m, okay, if and only if G has a vertex cover of size at most k. Okay, so that alpha satisfies this. Pick vertices corresponding to alpha in the matching edges. Okay, these are called matching edges, or you can also call variable gadgets. Matching edges slash variable gadgets, right? So I pick these guys. Now since this is a satisfying assignment, what does it mean? From every clause, one guy is same as what you have picked. From every clause, there is one literal which is same, because what is it? Pick vertices corresponding to alpha in the variable gadgets. So if alpha has set this to be 1, so you pick this. If alpha set this to be 1, you pick this. If alpha set this guy to be 1, because we have a bijection, right? So given alpha, I know which assignment I am talking about, right? We had a bijection. So now you came up with any alpha, I can go and map them. This is why I had this bijection that I don't have to worry about. So this I showed in the beginning itself, before even adding a clause gadget, that if you give me alpha, I know which one to which. So from every one you have picked one. Now what is the property? They are satisfying assignment. It means from every clause, one of the guy must be taken care of. So if you delete it from each xi, you delete these guys. So at least from every clause, the guy which is the variable which makes it to be truthful gets away. It may be that there are more people who are making, that's fine. But I know for sure that from every, after we delete vertices from the variable gadgets, we have that every triangle has a vertex with no edges to any variable gadget vertices, right? This is what we showed. Once we delete this, every triangle has a vertex which does not have any edge to variable gadgets. Why? Because the guy who is setting it to be true takes care of this. Then this is fine, right? Now pick the other two. So now to make a vertex cover, so now for vertex cover, now from each triangle select two vertices, okay, two vertices such that it covers all the edges incident on it, and since it looks like this is how it looks like, right? We can always select boxes from each of the triangle and we will be done. That's a property we had, okay, and now we have to prove the reverse direction of this proof, right? Now we have to show the reverse direction. Yes, if we had an assignment, we did this, right? Now notice everything is very tight, right? Everything is very tight. So every triangle, if you notice, every triangle has how many edges going out? Every vertex has one edge sticking out to the variable gadget. Okay. Now let's look at the proof for the reverse direction. Okay. What is the reverse direction? Let's see. Let C be a vertex cover of G of size at most k, right? By our choice, k is equal to k. By our choice, cardinality of C is actually equal to k, because locally you have to pick this much, so you have to pick this exactly equal here. Now what I want to say, okay, this implies, okay, furthermore, C intersection variable gadgets is equal to n, which implies for every triangle, there is a vertex. Okay, I don't have to do anything at this point of time. Let's go back. Furthermore, C intersection variable gadget is equal to n. Okay. So now I give a map, alpha from V to 0, 1, right? I had a bijection, man, right? So since you are going to pick exactly one, so this is a kind of state. So from this state, I can derive my assignment. This is how I made in the beginning. State corresponds to an assignment, assignment corresponds to an state, right? So now how do I say, okay, what is it? Alpha of x is 1 if alpha of x is 1 if, say, some alpha of xi is 1 if C intersection xi is equal to, C is my vertex cover, 0 otherwise. Basically this is what I am doing, right? So xi variable or the matching edge xi bar, that's it. So look at this, which one has been picked? If this is xi, you set it to 1, 0 otherwise. This is my assignment. Claim alpha is a satisfying assignment. Let Cj be a clause and triangle J be the triangle corresponding to it. Okay, and what do we know about triangle of J, right? Okay, C intersection triangle of J is exactly equal to 2, right? Let W be the vertex in triangle J that is not in C, that is not in C, that is not in vertex cover. What is the property of this? Right? What is the property of this? This implies, look, that's W, right? Whatever this literal is, W, right? So if W equal to some xt, say some xp, then we have an edge. I should have called something, okay, fine. Let's, okay, then we have an edge between xp and xp of variable gadget, right? xp and xp bar. We have an edge, right? Which implies what? Since it's a vertex cover, you did not pick W, you have to pick all its neighbors. So in particular, you have picked xp, right? This implies xp is
equal to 1. Alpha of x is equal to 1.
alpha of xp is equal to 1, and you are happy, right? So this is it. So now what did you do? So what is the whole engineering mechanism is, for every variable you take a gadget, basically take a Cartesian product of all these gadgets. Now that will give you a bijection between assignments and state space. So whenever you have to go forward, you just take this, you go to the particular assignment that forces you something, that will be your object. In the reverse direction, because the way you choose things, there will be a selection, there will be a state in which your graph looks like, or your variable gadgets looks like. Whatever it is that will correspond to an assignment, pick that assignment and prove that's correct. That's it. So this is the way you prove it. Nothing, there's no this thing. Fix a state, fix an assignment, show that assignment is what you wanted, and that's it. So once you have given this bijection, there's nothing. So you always keep in your head that, oh, I have to give a bijection, I have to give a bijection, I have to give a bijection. And if you're not giving a bijection for some region, then you should be knowing the mapping. These states corresponds to this, right? There are many ways of doing things in life, right? I have told you where there is bijection, but maybe the right way is that lot of assignments go to the same state, but you should so given a state, you should be able to know which all assignments it could correspond to. So you should be able to, you should have a mapping, right? Similarly, it could also be that lots of you can number of states should never exceed the number of assignments, right? So they all could go and collide, but you should know which, if this is a state, which all potential assignments it could be, and one of those assignments should be able to take care of your algorithm, and that is what it should be, right? Okay, so it's 15:30. I will leave you for today, and we are not going to continue because I'm tired.